Today we are going to see the second part of the lecture on vibration of one-dimensional monatomic linear lattice. In the first part of this lecture, you have seen a, a very important result which is called dispersion relation. And as I have told you in that very lecture that in we will discuss the dispersion relation in the second part. So today our aim is to discuss the result which we have obtained in the first part of this lecture. Okay. So here I have mentioned the final result which is called actually dispersion relation in case of the vibration of one-dimensional monatomic linear lattice. Actually you have seen that taking the Hooke's law and the Newton's second law of motion under account and considering an acoustic wave passing through a linear lattice, we have derived the expression for the angular frequency of vibration of the lattice. And that frequency is given by this relation. And you have already seen it, the derivation of this result in the first part of the lecture. What we have learnt, you can see here, we have obtained the result omega is equal to a square root of 4 mu over m times sine Ka by 2. I hope as you have learnt all these things in the first part of the lecture, so are very acquainted of this result. And for your convenience, although I have mentioned here, you know, this omega stands for the angular frequency of vibration of the lattice, okay, which is just equal to the frequency of the wave passing through the lattice. Because according to classical physics, the frequency of the system with which it vibrates is same as that of the agent which execute that vibration. So as the atoms of the linear monatomic lattice was vibrated due to the disturbance produced by the acoustic wave passing through it, and we have considered that the frequency of the acoustic wave was omega, and so the frequency of vibration is also equal to omega, and that omega is equal to what we have obtained already in the first part of the lecture, which I have mentioned in this result A. Okay. So omega is the frequency of vibration, you can say, or it is the frequency of the acoustic wave which disturbs the linear lattice. Okay. In this expression, actually this mu stands for force constant. M is mass of each atom of the lattice. As you know, in case of monatomic linear lattice, the mass of each atom or ion are equal, and that is equal to m, we have assumed. Okay, and here k is for wave vector. This symbol denotes the wave vector, or you also call it propagation constant or angular this is also known as angular wavelength, angular wave number. Okay, so what the different quantities in this expression refers, you can see it here. Okay, actually here you can see that this omega varies with this k. Apart from this k, everything is constant for a given lattice. So omega is a function of k. And how this omega varies with k, I have shown graphically it in the previous lecture, but again I have drawn that same graph here for your convenience. Here in this figure you can see the variation of omega in against of k. Okay, since it varies sinusoidally and omega cannot be negative, frequency is never negative, it is always positive, so the curve does not go into the negative side of omega in this figure. As you can see, when k is equal to 0, omega is 0, because when k will be 0, here there will be sine 0, and sine 0 is 0. And as the value of k increases, omega increases, and when this k is equal to pi a by 2, when k is equal to pi a by k, pi over a, then you know what will be this sine ka by 2. This will be equal to sine pi over a times a over 2. Here a and a will cancel out, and this is sine pi by 2, which is 1. And similarly, in the negative side too, actually when k is equal to minus pi by a, then again this will be maximum, and so this represents actually the maximum value of the frequency, which we denote by the symbol omega max. Okay. So at k equal to plus pi by a, plus pi over a, and k equal to minus pi over a, this omega is maximum. Okay. And after this, when k increases, the value of this sine function decreases, and when k is equal to 2 pi over a or minus 2 pi over a, then there will be sine pi. Okay, and sine pi is equal to 0, and so this omega becomes 0. And in this way, periodically this function varies with k. Okay, so this relation actually, this graph actually shows the variation of omega in against of k, or you can say the how the frequency of vibration varies with the wave vector. So this is the graphical plot of the dispersion relation. Okay, actually you have also seen in the previous lecture that the region between k equal to minus pi by a to plus pi over a, this is called first Brillouin zone, and the region in the two sides which lie between pi over a and 2 pi over a, this is actually the second Brillouin zone, and also the region between minus pi by a to minus 2 pi by a, for these values of k, you get again the second Brillouin zone. Okay, these things we have actually seen in our first part of the lecture on the vibration of monatomic linear lattice. Okay, now actually our aim in this second part of the lecture is to discuss this very important result, that is the dispersion relation. So we will see the important points of discussion regarding this result, or regarding the monatomic linear lattice vibration. So in our first discussion point here, we are considering the frequency is very low. If you consider that omega is very small, and as you know, when you say that omega is very small or frequency nu is very small, since omega is inversely proportional to wavelength. Okay, so when omega is extremely small, this lambda will be extremely large. In extreme condition, if you consider that this omega tends towards 0, then this lambda will tend towards infinity. And in this very condition, what will happen to the value of k? As you know, k is equal to 2 pi over lambda. And as we have assumed in this extreme condition that frequency of vibration is tending towards 0, and in that very condition the wavelength lambda is tending towards infinity, then what will be the value of k? k will be 2 pi over lambda, but since lambda is infinity, so you can say that in this limiting condition k will tend towards 0. Okay, and when k will tend towards 0, what will happen to the value of sine ka over 2? As you know from calculus that limit theta tends to 0, sine theta is equal to theta. Okay, so here since k is tending towards 0, so ka by 2 will also tends to 0, and in this limiting condition sine ka by 2 will be simply equal to ka by 2. Okay, so if you consider that the frequency of vibration is extremely small, it is almost 0, or in other words you can say that it tends towards 0, then what will happen to the dispersion relation which we have obtained in previously? So let us see. In this limiting condition, if you want to find the value of omega, what will happen? You have to put Ka by 2 instead of this sine Ka by 2, because you have seen that in this very condition sine Ka by 2 becomes Ka by 2. So the dispersion relation now is written like this: omega is equal to a square root of 4 mu over m times Ka by 2. Okay, here a square root of 4 will be 2, and that 2 and this 2 in numerator will cancel out, and your result will be omega equal to Ka times a square root of mu over m. Okay, so you can say that in this condition this omega is directly proportional to k. But if omega is directly proportional to k, what will be omega by k? That will be constant, and from this result you can also see that omega over k will be equal to a times root over mu over m. And for a given lattice, this a is constant and mu over m is a constant factor, so this is actually constant. So what happens here? You can see that in this extreme condition, when you consider that the frequency of vibration is very small and the wavelength is very large, actually in that condition omega over k remains constant. But what is this omega over k? You have definitely an idea. Actually this omega over k is the phase velocity of the wave. This is called what? This is called phase velocity Vp. And so in this case you can say that the phase velocity of the wave will be constant or independent of wavelength. And if velocity of the wave does not vary with wavelength, then the medium is called non-dispersive. It means no dispersion effect takes place in this very condition. Or in other words, you can say that the dispersion effect will be negligible. Okay, all these things I have mentioned it here. You can see that in this extreme condition the velocity of propagation of the wave Vp, which is omega over k, that will be equal to a times root over mu over m, that is equal to constant, that is independent of wavelength. So the dispersion effects are negligible. Okay, for an example, when this situation will you can see in practice. Actually, if at the place of a linear lattice whose atoms are separated by a constant distance a, you have assumed in the theory previously. But if we now consider that our monatomic linear lattice is just like a string where the atoms are not separated but they are in contact of one another. In that very condition, A will tend to 0, and when A will tend to 0, then actually the wavelength lambda will tend towards infinity, and we will get the situation which just I have told you. Okay. So for long wavelength, so you can say that this happens in continuous string. Such a situation is found in case of continuous string. Okay. And so you can say that for long wavelengths, the periodicity of the lattice is of little importance, because here in this case there is no periodicity of lattice, and so the periodicity of lattice does not matter in this case. Okay. But if you consider that this lambda is not tending towards 0, but now it starts increasing. When lambda will start increasing, then this, sorry, not lambda, but k starts increasing, then lambda will start decreasing. Okay. And in that very condition, you cannot neglect the dispersion effect. Then dispersion effect will be of great importance, that will be effective. And so as k increases and hence lambda decreases, dispersion effects become important, and we cannot ignore, we cannot neglect it. And in this condition, as you have told, that this omega is proportional to k in case of very small frequency or very large wavelength, but in this very condition omega will not remain proportional to k. Okay, it will be not proportional to k. Okay. So what happens when we consider the frequency of the vibration is very small or the wavelength is very large? You have clearly understand as I think. Okay. Yes or no? Have you understand or not? Definitely you have understand. Okay. Now, as you have seen in the dispersion relation curve that I have told you, the region for which this minus pi over a is less or equal to k, and this is less or equal to pi over a, this very region is called first Brillouin zone. Okay. You have already studied the concept of Brillouin zone in my previous lecture. Okay. And this region which lies between k equal to pi by a to k equal to 2 pi by a, and also k equal to minus pi by a to k equal to minus 2 pi by a, you know, these are actually called the second Brillouin zones. So now we will learn about this Brillouin zone. Actually at the boundaries, a very important idea will be obtained when you will discuss it. And as you have learnt in the first lecture on this subject, that when the wave passes through the linear monatomic lattice, the vibration is set up into the atoms. All the atoms start vibrating about their equilibrium position, and we have considered that a plane progressive wave is passing through it, and in that condition the displacement of any nth atom at any time t is given like this. You have seen this result or this equation in the first part of the lecture, so I have directly written it here. This un actually refers the displacement of the nth atom at any time t from its equilibrium position, and this un is given by a times e to the power I k n a minus omega t. You can remember it because you have seen this formula in the previous lecture, so you can remember. Okay. Now we consider a particular value of k, which I am denoting by the symbol km. And how this km is defined? We consider that this km is equal to k plus 2 pi m over a. Okay, we consider it. Here actually m is the positive and negative integers. You can see m is equal to plus minus 1 or plus minus 2, plus minus 3 and so on. Okay. Now we will see what will happen to the displacement un and the frequency omega when we replace k by this km. It means if you consider now k is equal to k plus 2 pi m over a, then what will happen to the value of un and the value of omega? Actually, we will see that neither the value of un nor the value of omega will change when we replace the k by k plus 2 pi by m, 2 pi m by a. Let us see how we can say this. Now we are going to find the value of un when k has been replaced by k plus 2 pi m over a. So in this condition un will be given by a times e to the power I, and at the place of k now I am writing k plus 2 pi m over a times Na minus omega t. Let us now simplify the RHS of this equation. You can see this can be written as a times e to the power I kNa plus 2 pi mn minus omega t. Okay, I have simply multiplied this Na, this factor k plus 2 pi m over a by Na. Okay, and this can be written as a times e to the power I kNa minus omega t times e to the power I 2 pi mn. Okay, but you know this factor e to the power I 2 pi mn is equal to 1. How you can say that this is equal to 1? Because you know this will be equal to cos 2 pi mn, okay, plus I sine 2 pi mn. As you know, m and n both are integers, and so the product of m times n will be also some another integer. Okay, and so you can write it as cos 2 pi n, capital N. We have assumed that this n is equal to mn. Okay, and plus I sine 2 pi n. But you know sine 2 pi n, this is equal to 0, and this cos 2 pi n, this is equal to 1. Cos 2 pi n is equal to 1. And so I have taken 1 at the place of this e to the power I times 2 pi mn. So finally we get that this un is equal to a times e to the power I kNa minus omega t. So this un remains same as it was when k is equal to k, as you can see in this figure. So you can say that when k becomes k plus 2 pi m over a, then the displacement of the atom becomes same as it was when k is equal to k. So you can say that at k equal to k, un, and at k equal to k plus 2 pi m over a, in this condition the value of un, both these un are same. Okay, both are same. So displacement of the atom becomes same as that when k was equal to k, and k is now k plus 2 pi m over a. Okay, now we will see what will happen to the value of omega. You will again see that even the value of omega will not change when you will replace this k by k plus 2 pi m over a. Frequency will also remain same. And for this what you will do? We will simply substitute k plus 2 pi m over a at the place of k in this dispersion relation. See here, this is your dispersion relation, and in this dispersion relation at the place of this k we will now write k plus 2 pi m over a, and then you will again see that omega is not affected, the value of omega remains same. But how you can now see it? I have substituted here, you can see omega is now equal to a square root of 4 mu by m sine ka by 2, but at the place of k now I am writing ka plus 2 pi m over a and times a by 2. Now again simplify the RHS. You can see the RHS can be written as a square root of 4 mu by m times sine what? Ka by 2 plus 2 pi m over a into a by 2. Now you can see this a and this a will cancel out, this 2 and this 2 will also cancel out. So this is a square root of 4 mu by m times sine ka by 2 plus pi m. But you know m is again integers, either 1, 2, 3, 4 and so on, both plus and minus. And sine theta plus n pi or m pi, you can say, this is equal to sine theta, okay, where m is equal to plus minus 1, plus minus 2 and so on. So sine ka by 2 plus pi m, this will be simply equal to sine ka by 2. So omega is finally a square root of 4 mu by m times sine ka by 2. And you can see this result is same which we have obtained earlier. So what you have found here? You have seen that when k is replaced by k plus 2 pi m over a, then un and omega do not change. Again at this value of k, un becomes same and omega becomes same. It means each and every particle, when k is equal to k and when k is equal to k plus 2 pi over m, are in same phase, or you can say that the motion of the particle is just repeated after this interval of 2 pi m over a for k, okay. So a state of vibration becomes same, okay. So I have mentioned it here, you can see that the frequencies corresponding to k and km, where km you know is equal to k plus 2 pi m over a, are identical. It means the state of vibration of the lattice corresponding to the wave vector k is the same as that for any wave vectors k plus 2 pi m over a, okay. So actually here you can say that this 2 pi over a, this is the period after which the state of vibration will become same, or you can say that this is the period after which the system repeats its motion, okay. So 2 pi over a is the period of this vibration, okay. And therefore if your aim is to find a unique relationship between the state of vibration and the wave vector k, you must restrict the value of k to a range of value 2 pi over a, because this is the periodicity of this function, okay. So now we are considering the range which will be equal to 2 pi over a, and we consider this range between minus pi by a and plus pi by a. You can see that this pi by a minus pi by a, this will be equal to 2 pi by a. So if you consider this interval of the for the value of k, this lies in the range of 2 pi by a. And as you have seen in the figure, that actually this region where k lies between minus pi by a and plus pi by a, this range of k values is referred as first Brillouin zone. Okay, this is called first Brillouin zone. And you have also seen that the second Brillouin zone consists of two intervals of half period each, and one on each side of the first zone. As you have seen that the one of them is pi over a less or equal to k, and this is less or equal to 2 pi over a, and another is minus pi over a less or equal to k, and this is less or equal to minus 2 pi over a. This is actually called the second Brillouin zone. Okay. Now you can see the value of k at the boundary of the first Brillouin zone is either plus pi by a or minus pi by a. You can see it here. These are the boundaries, and at the boundary in positive side, the value of k is pi by a, and in negative side this is minus pi by a. So the maximum value of k at the boundaries of this first Brillouin zone is plus minus pi over a. Okay, this is the value, and this k max is actually of the order of 10 to the power 8 centimeter inverse. This is order, something will be multiplied. Okay, so if you consider that this k max is of this order, then what will happen if you consider the continuous medium like a string? As you know, in case of a continuous medium like a continuous string, a tends towards 0, and you can see if 8 will tend to 0, then what will happen to the value of k max? Definitely you can say, since 8 tends to 0 in case of continuous medium, for example a continuous string, then k max will tend to infinity. Okay, k max will tend to infinity, as you can see. Okay, again at the boundary of the first Brillouin zone, you have seen that k is equal to plus minus pi over a. So now we are going to find the value of un, that is displacement of nth particle, at the boundary of the boundaries of the first Brillouin zone. Okay, so for getting the value of un at the boundaries of the first Brillouin zone, we will simply replace the k by plus minus pi over a in the dispersion relation. Sorry, not dispersion relation, in the expression for un. As you know, un is equal to a times e to the power I kna minus omega t. So if your aim is to find this un at the boundaries of the first Brillouin zone, what you will do? You will simply replace this k by plus minus pi over a. Okay. Now you can see this a and this a will cancel out, and your result will be a times e to the power I plus minus n pi minus omega t. Okay, and this can be equivalently written as a times e to the power plus minus I n pi times e to the power minus I omega t. But this e to the power plus minus I n pi, what is this? You know, e to the power plus minus I n pi, this is equal to cos plus minus n pi plus I sine plus minus n pi. But you know, sine n pi, this is equal to 0. because you know if n is 0, sine 0 is 0. If n is 1, sine pi will be 0. If n is minus 1, sine minus pi, which is minus sine pi, that will be also 0. If n is 2, sine 2 pi, you know this is 0. If it is minus 2, then that will be minus 2 sine 2 pi, but sine 2 pi is again 0. So this will be cos plus minus n pi. But you know cos minus theta is equal to cos theta. Okay. So cos plus minus n pi is simply equal to cos n pi. And what is this cos n pi? You know, if n is equal to 0, 2, 4, 6, that is even number, then cos n pi is equal to plus 1. But if n is equal to 1, 3, 5, 7, then cos n pi is equal to minus 1. So in general, you can say that cos n pi is equal to plus minus 1. Plus minus 1. And so this equation, which I have mentioned here, that can be written as, instead of e to the power plus minus I n pi, we can now write cos n pi or plus minus 1. You can also write equivalently it plus minus a e to the power minus I omega t. You can write it. Okay. Actually, this equation represents a standing wave or a stationary wave, okay, in which the atoms vibrate in opposite phases, alternate atoms. As this plus minus sign represents what? Actually, if you assume that there is a these are the atoms of a monatomic linear lattice. So when this atom will move in upward direction, definitely this atom will move in downward direction, this will also move in downward direction, and again this will move in upward direction, then these two particles will move in downward direction. So this plus minus sign actually refers that the alternate atoms vibrate in opposite phases. Okay, this is a very remarkable fact. Okay, and this happens at the boundary of the first Brillouin zone. Okay, actually you have learnt in very detail in my previous lecture the Bragg's reflection, the concept of Bragg's reflection. So this formation of a standing wave, this is just analogous to the Bragg's reflection of X-rays, because you know when Bragg's condition gets satisfied, then a wave cannot propagate in a lattice, but it undergoes successive reflection back and forth. Okay, so as when Bragg's condition is satisfied, then you know when the electromagnetic radiation or wave is incident on a crystal, the wave does not pass through the crystal, but it suffers multiple reflection and a standing wave is just formed. Similarly, in the situation is just like that. This is the boundaries of the first Brillouin zone, and a wave will incident on the first boundary and that will get reflected. Again this will incident on the second boundary and this will get reflected. So I have told you that this situation you can compare is just equivalent to the Bragg's reflection of X-rays, because in when Bragg's condition is satisfied, the wave does not propagate through the crystal, but it suffers successive reflection back and forth. And similar is the situation in this case too at the zone boundaries. Okay. Now you can see that this fact which I have just explained, uh, how we can say analytically that when Bragg's condition will be satisfied and the wave does not propagate, the similar situation takes place in this case of lattice vibration too. Now see it in a quantitative manner. So you know this is the value of k at the at the Brillouin zone boundary, that is k max equal to plus minus pi over a. This is the value of k at the boundaries of the first Brillouin zone. Okay. Now we will see that this, if you take k equal to this much, then Bragg's condition will get satisfied. You can see. You know, Bragg's equation you have studied. According to Bragg's law or Bragg's equation, 2d sine theta equal to n lambda when the intensity is maximum. This equation is called Bragg's equation, or this is also called Bragg's law. But in case of the monatomic linear lattice, this d is equal to a, okay, and theta will be equal to pi over 2. Theta is equal to pi over 2, because in this condition the wave, the lattice is monatomic, it is just like a line. So in this case, this glancing angle theta is equal to 90 degree. And for the, if you consider the first order Bragg's reflection, in that condition when n will be equal to 1, which is its lowest value, then actually you will get the minimum value of this lambda. Okay. And what will be that? If you substitute these values in this result, you get 2a sine pi by 2 equal to lambda, and so that you can say lambda is equal to 2a. Actually, I have told you that this is actually the minimum value of lambda, so you can say that lambda minimum is equal to 2a. Now, once you know the value of minimum lambda, now you can find the maximum value of this k, because you know k is equal to 2 pi over lambda. So if your aim is to find the maximum value of k, you have to put here lambda minimum, then you will get k maximum. So k max is equal to 2 pi over lambda minimum. But lambda minimum, you have seen this is equal to 2a. So at the place of lambda minimum here I have substituted 2a. Now this 2 and this 2 will cancel out, and your result is pi over a. Okay. But as you know that the wave can propagate both in both positive and negative direction. So taking the direction of propagation of wave under account, we can say that this k max is equal to plus minus pi over a. So in this way you can see that if Bragg's condition is satisfied, then we have obtained that k max is equal to plus minus pi over a. So in the reverse manner you can say that if k max is equal to plus minus pi by a, then definitely Bragg's condition will be satisfied, and if Bragg's condition is satisfied, there will be no propagation of the wave, but a standing wave will be formed inside the lattice. Okay. So this was all about the Brillouin zone in case of the vibration of linear monatomic lattice. Now we will discuss a very important fact regarding this vibration of monatomic linear lattice. Actually, you will see in this point of discussion that this monatomic linear lattice behaves like a low pass filter. When you say low pass filter, this filter is actually studied in the course of electronics, and if you have studied that thing, you have seen that in case of low pass filter, the circuit allows only the frequencies up to a particular value, which is called actually the cutoff frequency. Okay. we will see it here in this case too, that all the frequencies of vibration are not possible, or all the waves and the waves with any value of frequency cannot be propagated through this lattice. There is an upper limit, you will see it here, and that can be actually found by starting from the equation which is called dispersion relation. As you know, according to dispersion relation, this omega is equal to a square root of 4 mu over m times sine ka by 2. Okay. Now we will find this omega corresponding to the value of k at the boundaries of the first Brillouin zone. So corresponding to the zone boundaries, k is equal to k max, and that is equal to plus minus pi over a. So in this condition, when k will be maximum, omega will be also maximum, you know. So omega maximum will be what? For getting the maximum value of omega, or the value of omega corresponding to the zone boundaries, we will simply substitute pi over a at the place of k, not plus minus, because omega is never negative. So we discard the minus sign. And when you will substitute it here, you can see this sign ka by 2, and taking k equal to pi over a, neglecting the minus sign, times a over 2. This a and this a will cancel out, and this is sine pi by 2, and that's equal 1. Okay. So in this condition, omega max becomes a square root of 4 mu by m times sine pi by 2. But as you know, sine pi by 2 is 1. So omega maximum is simply equal to a square root of 4 mu by m. Okay. Now if you want to find the corresponding regular frequency denoted by the symbol nu, then nu max, you know, will, since nu is equal to omega over 2 pi, so nu max will be equal to omega max over 2 pi. Okay. But omega max you have obtained in this equation 4, so let us substitute that value here, and you will see that this nu max is equal to 1 over 2 pi times a square root of 4 mu by m. But a square root of 4 is 2, and that 2 and this 2 will cancel out, and nu max is equal to what? This is 1 over pi times root over mu by m. Okay, mu by m. So this is the maximum frequency that can be passed through this linear lattice. This is the upper limit, or you can say this is the cutoff frequency. So you can say that our monatomic linear lattice will allow or only those frequencies which lie between 0 and nu max. Okay. So you can say that there exists a maximum frequency nu max, the wave corresponding to which can propagate through a chain. Thus, a monatomic linear lattice transmits the frequency in the range 0 less or equal to nu, and this is less or equal to nu max. And this is actually the characteristic of a low pass filter, and that's why we simply say that the monatomic linear lattice acts like a low pass filter. Acts like a low pass filter. Okay. Now, from this result we will get something more. You can see it here. As you know, how the frequency and the wavelength are related, because the wave velocity v is equal to nu times lambda. So nu is equal to v over lambda. Here v is actually the wave velocity. Here we are considering the acoustic wave, that is the sound wave. So you can say that this v is the velocity of sound wave. Okay. And nu max is the frequency, lambda minimum is its minimum wavelength. But just we have learnt here that this lambda minimum is equal to what? Lambda minimum is equal to 2a. Just we have obtained, you can see, definitely I have obtained it earlier. See here. I have obtained earlier, you have seen just now that this lambda minimum is equal to 2a. Okay, lambda minimum is equal to 2a. So at the place of this lambda minimum, I have put it here 2a. Okay. Now you know, in case of a crystal or in case of a lattice, this interatomic separation, this is of the order of 1 angstrom, that is 10 to the power minus 10 meter. And the velocity of sound in solids is of the order of 10 to the power 3 to 10 to the power 4 meter per second. Okay, the page has been turned, but this will be just okay, you can see. Okay, so V is of the order of 10 to the power 3 to 10 to the power 4 meter per second. So when you will substitute this in here, what will be the value of nu max? You can see, if we take V of the order of 10 to the power 3 and A of the order of 10 to the power minus 10, this will be of the order of 10 to the power 13. Okay, and when you will take V of the order of 10 to the power 4, then it will be 10 to the power 14. So nu max is of the order of 10 to the power 13 to 10 to the power 14 second inverse. Can you say, after seeing this order of frequency, that this frequency lies in which region of the electromagnetic spectrum? Definitely, if you have an idea of the wavelength and frequency of different region of the electromagnetic spectrum, you can say it. Actually, this is the order of frequency of the infrared region. Infrared region. So you can say that the cutoff frequency lies in the infrared region. Okay, in the infrared region. But if you now consider again the continuous medium, for example, you are considering a continuous string, then you know A tends to 0. And if A will tend to 0, see from this result. When A will tend to 0, what will happen to nu max? Nu max is equal to V over 2A. And you are saying that A is tending toward 0. So definitely you can say that in this condition, nu max will tend to infinity. So in case of continuous medium, there is no upper limit, defined upper limit of the wave that will propagate through the lattice. So in this case, you can say that there is no upper frequency limit. Okay, but if the medium is not continuous, then the upper frequency limit, which is called cutoff frequency, that can propagate through the lattice, lies in infrared region. But in case of continuous medium, any frequency can excite the atoms of the medium to vibrate. Okay, and so there will be no cutoff frequency. So I have discussed the 3 very important points regarding the vibration of monatomic linear lattice, and I hope you have clearly understand all the points of discussion. So I will suggest you go through the video seriously with pen and paper in your hand, write down everything and revise it. Definitely everything will be crystal clear to you. Okay, thank you very much.